All right, today we're going to continue chapter 4, section 3, which is called monotonic functions. And the first derivative test. Then we're going to discuss section 4, which is called concavity and yes. And curve sketching. Monotonic functions. What do you think monotonic functions are?
Well, mono is one. So tonic, I feel like that could be.
It's a drink. No.
Yeah, well, that's true, but maybe related to time.
Then no, I see how you get tonic. No, it simply means that it's well structured, like it's either increasing or it's decreasing. It's just not.
But it doesn't turn. Like it doesn't.
Well, it does turn. It turns slowly though. If it's like the E function, e to the x, it's a very monotonically increasing or decreasing function, depending on what the exponent is. So I'm glad you said turns, because that's what we're looking for here. Because up until now, in algebra, we learned the basic crap. I can print out because that's one of the things that's in the print queue. I put my card on there and it goes copy card not recognized. I just used it this past weekend. So yeah, I showed up Saturday for my class and nobody showed up. Nobody, period, not in my class, not anybody's class because of the rain.
Oh wow! Oh yeah.
I came right in the middle of the whole thunderstorm and everybody else had 2 power outages. So anyway, we know by looking at the function what it looks like by just algebraic observation. What else do we need to know? We learned on how to find the vertex. So how do we find the vertex?
The vertex, you just need to find the x value.
Yes, but what x value? What exactly is a vertex?
It's the point, the lowest point.
Or
The highest.
What's the slope at those points?
0. To find the x value makes it 0.
Right. Those are the x values of the vertex. Basically, you say if it's quadratic, you say it's axis of symmetry. But yes, those are the x value of the vertex. Once you find that, then plug it back into the equation, and that finds you the y value of the vertex. So if we had a cubic function, we have a function that looks like this. So if this is a vertex and that's a vertex, let's call that C1 and C2. What do we know? How do we prove that that's a maximum? Because we know it's a vertex because the first derivative at C1 equals 0. You know, it's a vertex. How do we know it's a maxima or minima?
You would have your interval So you would have, C1.
Well, we look at everything to the between these, all of these. Look at all those open intervals. So to the left of C1 in this graph, what would we expect to find?
Negative.
Well, in this, yeah, but more so since we're talking about the first derivative, what will we find over here? The first derivative of these x values are all positive. Why are they positive? Because going from left to right, that graph is going up. It's getting higher and higher and higher. Then it's 0, and then the first derivative becomes negative. It goes down until it gets to here, where it's 0 again. Then it starts going up. So the first derivative of these x values will be back to being positive. So we can determine on where a function is increasing or decreasing. It's increasing if the first derivative is greater than 0. It's decreasing if the first derivative value at that x is negative. Let's put this into terms of camping or hiking. Increasing means going up the hill. Decreasing means you're going down a hill. If the instructions were go up the hill, and then keep on going, and now you're going down the hill. What did you just reach, a valley or a peak? If you're going up the hill, then you're coming back down the hill.
You just reached it.
Yeah, you keep on going forward. You're going up the hill, and now you're going back down the hill. So you reached a peak. It's the maximum. It's the highest point. As opposed to you're going down. All of a sudden now you start going up. When that happens, you have a minimum. You have a valley. So that's what we're looking at here as the direction of the graph relative to the first derivative test. Rich, this is the first derivative test. If you take the first derivative of a function and place a value, any x value in there, then you can determine by the solution of that whether it's an increasing or decreasing or a vertex point. How does all this stuff relate back to tangent lines?
The tangent lines have a slope of around 0.
No.
Well, those are the tangent lines.
No. That is one, but it's not true for everything. Because remember, what does the first derivative find?
The slope at a point, or well, it finds the formula that gives the slope.
The slope of the line tangent to the curve at a single point. That's what it finds. Because remember, when we first defined slope, we talked about the linear equation of slope. So for example, if we found a point here, when we say these increasing or decreasing part, what this is saying is the slope of the tangent line is increasing at that point. The slope of the tangent line is decreasing at this point. So that's what all this stuff means. And that's why we spent so much time in chapter 2, because it defined all of these, what they were. Yes, it is a slope. We found it by finding the difference quotient and the limit of the difference quotient as h goes to 0. And then what that really means is this, because now we find the slope at any given point of any curve. So how would you find absolute and local minimas and extrema?
You would have to use the theorems.
Yes. So let's say in here we have two extrema here. How would we know if one's a maximum minimum without using the slope part here? Because yes, we know that it has to be an extrema because the slope is equal to 0. But how can we tell if it's a relative, local, or absolute, or global extrema? Go back to the algebra part.
Well, if they have different signs.
You're getting yes.
So if they have different signs, then F or C1 and C2, we know that there's going to be a minimum and maximum.
Right. How do you tell which one is which?
You have to,
without having the graph. Because once you set the equation equals 0, you found C1 and C2. Those are the x values in which the first derivative equals 0. Take these values, plug them back into the original equation. If f of C1 is greater than f of C2, then f of C1 is the maximum. Else f of C1 is the minimum. This is similar to flying instruments as opposed to visual on an airplane, in an airplane. What this is showing us is we can find all this stuff by just the numbers. We're not looking at anything else. But if we look at a graph, f of C1 is this point here, f of C2 is this point here. Since this one's higher, this is the maximum. F of C2 is lower, so it's minimum. And that's what this is saying. Since they're f of C1, f of C2 are both extrema, one of them has to be maxima, one of them minima. They both can't be maxima. Actually, or can they? What if we had a fourth order equation? C1, C2, C3. It is possible to have two minima. Why?
Because it's over, a specific interval.
We're looking here locally. This one's minimum of this interval. This is in that interval. And so we're looking at local. Globally, we have no minimum. Because you only have one absolute,
Because they're equal.
right? But we don't even have a maximum because both of these ends go up. We only have local or relative minima and maxima, extrema. All right, let me see. Okay, yeah, let's go ahead and graph one. I don't have any worksheets with me because again, I couldn't print out the examples. So we don't have anything to do inside here, so I'll make up something. Let me see. All right, so it's going to be so we have cubed minus 5x squared minus 10x minus 24. Let's go ahead and graph this one with everything we know so far.
So we can plot the origin first, I guess.
Well, we have the graph. I mean, we have the XY chart. So what would you do first? What's the only point you know right now?
The minus 24.
Right. And that is where? It's all the way down here at negative 24. It's a y-intercept. So there's a break. Right. What else do we know about this function? What is
X
It's
to the, yeah,
so what does the leading term tell us?
that it's gonna call it. It's gonna go downward on one side and upward on the other.
Yes, the end behavior, right. Because it's cubic, we know that both ends point in different directions. Since A, the leading coefficient, is greater than 0, we know the left side goes down, the right side goes up. It's an increasing function. So that we know so far. So from the farthest left endpoint, the 0 goes down. For the farthest right, it goes up. We just have to find the x-intercepts now. How do we find the x-intercepts? Yeah, but we really can't factor. If we factor this one out, we have 5.
Find the, so
If you find the first derivative equals 0, what does that give us? Right, so it gives us the vertices. We'll have to do that eventually. So what would the first derivative be? Well, let me verify this, make sure it's going to work. X cubed, x negative 6. Ah,
6.
it can be a positive 3x. Let me check this. Yeah, so I want to make sure it's going to work. So it's x cubed minus x squared minus 6x. 4x squared. Okay, that should work. Okay, so the derivative, okay, this derivative is going to give us not 10x, it's going to give us positive 6x in the middle and negative 10. One thing from calculus 1, what do we know? I mean, from algebra, this is calculus 1. How do we find the x-intercepts of a polynomial?
But you either use the quadratic formula.
Not with cubics.
Oh, for this, okay, well, you factor out x, or well, maybe you don't factor out X. So you have to,
And we can't use the um,
the quadratic.
grouping method. Yeah, quadratic formula here. We can't use grouping because if we factor this one out, all we can take out is 2, we'll have 5x minus 12. And that's not going to give us an x plus 3. So we got to use Descartes' rule of signs as well as the rational zero theorem. This is P and this is Q. We have to look for all the possibilities of Q over P. And then see which one of those are zeros. So 24 over 1. What are all the possible factors of 24? 1 times 24, 2 times 12, 3 times 8, 4 times 6. All over 1. Because leading coefficient is 1. So what that means is our answers can be plus or minus 1, plus or minus 2, and so on and so forth. So how do we test it? Synthetic division. Yeah, so let's try positive 1. 1, 3, negative 10, negative 24. One times 1 is 1. Add those. 3 plus 4. 1 times 4 is negative 6. 1 times negative 6. So it gives us negative 30. So 1 doesn't work. Then we try negative 1. 1, 3, negative 10, negative 24. Bring down the first one. Negative 1 times 1 is negative 1. 3 minus 1 is 2. Negative 1 times 2 is negative 2. Negative 12. Positive 12. So -1 doesn't work. So 1 doesn't work. We have to try 2 now. 1, 3, -10, -24. 1 times 2 times 1 is 2. That gives us 5. 2 times 5 is 10. So that one doesn't work. So we'll try -2. -2 times 1 is -2. 3 minus 2 is 1. -2 times 1 is -2. 10, -10 is -12. -2 times -12 is +24. Yes. So we found our first zero. X equals -2. Which means that X plus 2 is a factor. Now all we have to do is look at this equation. This is the constant, this is the X, this is X squared. So we have X squared plus X minus 12. We can factor those. So what makes up X squared is X times X. The second sign is negative, so that means the signs are opposites. And the bigger number gets the plus. What times what equals 12? When you subtract them, you get 1. Now, forget the negatives. 4 times 3 is 12. 4 minus 3 is 1.
Oh, okay,
So-
positive.
4 gets a positive, 3 gets a negative. Set those both equal to 0. So these are my other two x-intercepts. And my other two factors. So we're at -4 and at +3. Those are our x-intercepts. From the leading term test, we know that the graph goes down here and goes up there. We also know, since our factors of our equation are x plus 2, x minus 3, and x plus 4, since the multiplicities of each one are odd, that means that the graph crosses at all of these points. So the graph will look something like this, and has to go down to 24.
And it's even at the top.
Right. If it's even, if it's an even number, then it bounces off that value. So we know that much already. That means we're going to have two real solutions. So now we look at, now we're going to find the vertices. Remember, the number of vertices is always one less than the degree. Since our degree is 3, we're going to have 2 vertices. We have to use this equation. We'll use -b plus or minus. You see how much of this stuff is algebra driven?
And a lot of
90% of it, yeah.
it. Yeah. It's really, it's like the calculus is just the concept and then everything else is.
Exactly. It is just the concept. It's the idea that behind it. It's again, it's just turbo algebra. It does some of the algebra much faster.
Well, basic calculus is basically like.
It's turbo algebra.
So it's
It-
like the magic.
Yeah, it's everything you do in calculus is algebra driven. Every one of the theorems, everything is proven by algebra. So what we have here now are A is 3, B is 6, and C is -10. We have -6 plus or minus 6 squared, 4 times 3 times -10 over 2 times 3. -6 plus or minus 36. Negative and negative is a positive. 12 times 10 is 120 over 6. -6 plus or minus 156 over 6. What is 14 times 14? 196. 13 times 13. $169. So it's lower than that. 12 times 12 is 144. So it's between 12 and 13.
It's, yeah, it's 2 and 49.
239. So we have -6 plus minus 2 root 39. So we can factor out a 2 on top. -3 plus minus root 39. So our our vertices are at -3 plus or minus root 39 over 3. So yeah, calculator root 30. What's it going to be on the negative side? -3 minus root 39 over 3.
-3.0.
And the positive side?
1.08.
Thank you. Yes. So 3.08, -3.08 is right there. And 1.08, which is pretty much where we expected it to be.
Yeah, it'll be pretty close estimate.
So once we find the x-intercepts, we find the vertices and connect them. Let's see what other topics here.
And then if we, when we plug those in, it will give us the minimum.
It'll give us the actual location.
And then we just, and we connect the curve like that.
Because once we have the x-intercepts, we have the vertices, then we know pretty much the exact shape of it.
And you just attach a smooth curve.
Mhm.
Is there like a technique that they used to use for?
Making it
connecting the
smooth?
curve?
Not really, because which that pretty much sums it up for that section. And we'll do the examples next time because I don't have the sheets here. But what happens here, somewhere along this and this path, a change happens. Because if you think about it, this is going down. At what point? Because think of an airplane, the pilot's going up, then it begins to dive. At what point does the pilot start pulling back to start going up? Because if you think about it, if the pilot's going down, here's 0. If the pilot's going down, he's doing a nosedive. And then eventually he's got to pull it back up, and he's back up to 0, and then he starts going back up. That's what's happening here at these points. And they have a special name too. And they have a special way of finding them.
Okay, are we gonna learn that? at some
That's section 2.4. Or yeah, concavity.
And those points, you need to know those.
Yes.
I'm assuming for a lot of aerospace stuff.
Yes, because that's the point. And I said where it starts bending this way and he starts bending that way. So if you're going to design something that somebody has to build, you have to know exactly when the curve stops bending.
That-
I'll continue from here. This is chapter 4, section 4. Concavity and curve sketching. Because if you think about it, I mean, each one of these tells us a different story. What does the f of x give us, the original function?
The position.
Or points on the curve. It gives us all the points, yes. Specifically, what points are we looking for with that function?
The first.
Not with that one.
Oh, yeah.
By looking at it, we know the x-intercept. That's the constant term. And we can find the x-intercepts. Set y equal to 0 and solve for x's. Also from this, we'll come back to this guy, from the leading term. The leading term, the term that has the x with the highest exponent, it tells us the shape and direction of the graph. So before we start graphing anything, we know what it's supposed to look like. We know from the leading term the shape and direction, x-intercept or across the x-axis, y-intercept or across the y-axis, and we can find a bunch of points. That's just from the original. Now, what can the first derivative tell us? Extrema points, where f of x is set equal to 0. What else can it tell us? Well, you go with slopes. Basically, we find intervals where the function is increasing or decreasing. Because that just goes from basic logic, because if the first derivative is set equal to 0, it's a horizontal line. So there has to be something on both sides, either going to be going up, then down, or down, then up. What else can we find from there? Nothing really. So that's what we've done. What's that? Was there anything else? So now we have to include the third stepbrother in this picture. Because remember, when we first start talking about derivatives, we talk about the original function, which is a position function, then the velocity, and then acceleration.
So it can tell us how quickly it's increasing.
Yes, but does that matter on the graph?
Well,
Well, I think you may have a point there. It may have a point with to do with the slope, the steepness of it,
okay, yeah. So
but that would also come from here. If it's first derivative, if it's a large number, it's very steep. It's a very shallow number. So yeah, maybe not, but it'll be worth looking into. It does do something else for us. It does two things. Tells us the concavity of the curve What is concavity?
kind of like the opening.
If it's like this, or if it's like this. This is concave up and concave down. So these are what you find from all of your second derivative of the function. Same as the first derivative. We found where it's increasing or decreasing by finding the derivatives. Well, that gives us is it concave up, concave down, the shape of the bowl. What about, can we set it equal to 0? It also tells us what's called the point of inflection. At the second derivative, set it equal to 0. Point of inflection is where the graph is neither concave up or concave down. It's a transition point between concave up and concave down. If you want an example, the airplane. This is the second derivative set equals 0. Diving, it's concave down. Going back up, eventually it comes to no concavity. Now it's concave up. That's what's happening here.
The inflection point on like, so if you have like half of that function, or like if you take off the left bounds and the right bounds, then you basically have like a tangent function, right?
Yes, and we'll talk about that because in tangent functions, because the graph of a tangent pretty much is like a whole series of
Right.
cubic functions.
So, because it's periodic, okay.
But yeah, with those
The inflection point, okay, yeah.
is right in the middle because where it stops being concave down and starts being concave up. In this one, it's the point somewhere in the middle where it stops being concave down and starts being concave up. That's the point of inflection. Let's find these now. Let's look at the examples that we've used earlier. Find me the point of inflection. Find me the point of inflection. Well, the first derivative is 2x plus 5. The second derivative is equal to 2. So what's the x value there?
Or two.
I see how you got 20,
Okay.
but no. The second derivative at x equals 2. Since this does not have an x, no point of inflection. Because remember, what is the point of inflection? The point where a graph does what?
Changing from increasing the curve to decreasing the increasing, or increasing the decreasing.
Right. That's essentially what a vertex does. But it's not, so we can't say increasing, decreasing. That's what vertices do. What the point of inflection does is where the graph changes from concave up to concave down. It's a point where they start changing.
But since that's constant, it can't.
Right. Because there's no x in there. Let's look at our last example that we had. So to graph this, you would have to first do the algebra of finding the x-intercepts, then find the vertices. So what's the first derivative? And the second derivative? So the point of inflection the POI occurs where? Tell me the location of the point of inflection.
Negative one. Negative one.
-1.
But I want a point of inflection, the point,
So you have to plug the negative one into the.
right? Yeah, it happens. The point of inflection occurs at x equals -1. Yes. By setting 6x plus 6 equals 0. So now we got to find the other point. So -1, which will give us -12. -1 plus 3 is 2. 2 plus 10 is 12. 12, yeah. So the point of inflection occurs at -1, -12. Well, from the last graph that we had, put it down here. In our last graph, we knew we had x-intercepts at -2, -4, and 3. Our vertices were at -3.08 and at 1.08. So at -1 and -12, at that point, the graph stops being this shape and begins this shape. At that point there, at the point of inflection. So all this stuff here, it's all pointing down. Then it's all,
Okay, now.
yeah, everything up until -1 is concave down. From -infinity to -1 is concave down. Everything. Then everything after -1 to infinity is concave up. Because I'm trying to understand, visualizing, trying to see what it really means. Think if you had two bowls and you put them just on their edges. Where they touch, that's the point of inflection. Where the two bowls begin, because this bowl's always going up, this one's always going down. Where they touch is the point of inflection.
What was our local, or minimum and maximum?
It was at -3.08 and at positive 1.08. We didn't do the Y values.
Can we point us like a turning point, like
It is a turning point. It's It's the point where it stops being down, starts going up, or conversely, going up from down. It is a turning point. But you can also say the turning point is the vertex. You have to be very careful how you're going to say it. So, because it's actually changing directions after the vertex.
Right, yeah.
Can a vertex be an endpoint?
I mean, if the interval, if there's an endpoint that says that it's an endpoint.
Think of the definition of a maxima, of a vertex. You have a maxima or a minima.
Has to be an open interval.
But if it's a maximum, what has to be true about it? On the left of it, it's increasing. On the right of it, it's decreasing. But if it's an endpoint, there's nothing on the left of it. All you have is to the right of it. So it's one of those philosophical type questions, and that's why you have extrema, but I don't know if you can call it a vertex.
So you don't think it
Endpoints, not endpoints. You can have extrema, maximum, minima, but they can't really be vertices because a vertex is a highest point.
It's gotta
of
have
both
two
sides.
things on the side. It has to be continuous.
Has to be increasing then decreasing or decreasing then increasing.
So would you say it has to be continuous? Like it has to have
All of them have to be continuous. Every function we have so far has to be continuous. Why? Because it has to be continuous because it has to be differentiable everywhere. Yeah, and then that was what we proved with the limit function. It has to be continuous because it has to be differentiable. But a limit doesn't have to exist to exist,
right.
which is very it's not a contradiction to itself.
So they can be,
Mhm. Right. And that's where we're gonna get to later on this. I don't know if we're not in this chapter, in next chapter then, but we're gonna look at limits or unbounded. We're gonna look at indefinite ones, indeterminate fractions coming up after we do the check section 3 and 4 homework, the sample problems, because section 5 is one of my favorite ones, indeterminate forms and L'Hopital's rule.
And that at that point you're starting to break into calculus too. For your
Pretty much, yeah, because from there on out we do optimization problems and then Newton's rule, Newton's formula, his method.
I asked ChatGPT about that the other day.
Well, see, what you do from now on, also do that, is I want to have a discussion every day about, are y'all know how to use ChatGPT?
I don't use it, but I've seen people.
I have
Yeah,
the Apple.
Okay, because I'll show you guys the prompts because anybody can ask questions. It's just that we were never taught to ask questions,
The way.
the right questions. Because remember, ChatGPT, all of AI, that's a misnomer. It's not intelligent because it only learns what we give it. And where does it get its information from? The internet. Well, does it ever cycle through all the WikiLeaks stuff that anybody can post whatever they want to? So no, it's limited in what its intelligence really can be. So what we'll start doing then on Wednesday is what I want you to do from now on is the rest of this course is at the beginning of each course, I want to see what you typed in, what prompt you used, and what did it tell you? Because I'm going to start asking you, what can you tell me about this topic? And so on Wednesday, I'll give you the list of stuff that I want to go over on the next course in the next class, so that we can discuss what's going on. Because again, I found out when I started playing with it, a lot of times when we ask people to do things for us, we're timid. We won't ask them to do everything we want them to do. We say, well, can you actually go clean that up for me? Not clean it up, polish it, but in ChatGPT, you're the boss. I mean, it doesn't have any feelings. That's the hardest thing you have to get over. Even though it says, if there's anything I can do, I'll be happy to help you. And you'll be saying thank you to it a lot of times. And it doesn't have any emotions, it doesn't have any feelings. So you have to know how to structure the prompt.
Be very specific.
You have to be very specific because, I mean, what I've seen so far, it's either 4 or 5 sections that you have to include in every prompt. And you have to be specific what you want. Because if you just says, if you ask you to just give me the derivative, it'll give you a derivative. It doesn't have to be right. You never said give me a correct derivative. So just give me a derivative. Because a derivative, the derivative to this function could be 7. It's a derivative, but it's not the right one. So you have to be you have to be more specific. You have to tell it, give me the correct, or give it a position. You are a university professor, calculus professor, math professor. Find the derivative and tell me how to find or how to solve this process. Because it's really good at giving you step-by-step procedures. I mean, it'll give you everything you need.
If you're stuck on the problem or something, it might not even be able to solve the problem itself.
But it'll give you the hint and clues how to get there. And that's because it's not made to do any real calculations. It's made to just give you maybe literal answers. But there are some things you could do to make it more mathematical friendly and do graphing and stuff.
It's kind of, I was reading an article about the, I was trying to learn about the interactive theorem provers,
Mhm.
like Lean and stuff like that. And they were saying a lot of the people when they're writing their proofs, they try and verify their proofs with Lean or with another